Hello, I am Saikante, a second year PhD student at Peace Lab in Arizona State University. Today I'll present my ongoing research on hybrid phase duty controlled loss optimization of a triple active bridge converter. Such a DC-DC converter can be used in multiple energy management systems such as space power supplies, onboard EV chargers, etc. This work is done in collaboration with Coolcat Electronics, and the work is partially funded by the National Aeronautics and Space Administration, NASA. Recently, the demand for versatile energy management system, which is capable of capturing and delivering energy to other energy source or sinks connected to the same architecture, is constantly increasing in order to enhance the modularity and configurability of the electrical network, such as in distributed renewable energy systems or in subsystems like onboard chargers or more electric vehicles. So these are all efficiency critical applications, and maintaining a low loss at wide gain and load range is very much important. The conventional phase modulated triple active bridge converter deals with a few challenges and problems. Uh, Mostly the approaches in research is based on the fundamental harmonic approximation of the bridge voltages, which lacks from the current analysis and voltage and estimation, uh, accurate voltage estimations. The phase modulated control of power flow um, lacks from the optimization of loss, and also it operates at singular operating point if I don't include any duty cycle variable in the system. So there is no scope for power loss optimization. The possible solution that we have discussed about in this paper uh, incorporates the bridge voltage duty cycle control as well as the phase control. We have approached the modeling from a generalized harmonic approximation point of view, which simplifies the quantification of the circuit currents and voltages and with accuracy. Also, we have approached the problem with a multivariable optimization framework to minimize the conduction loss in the system. The generic architecture of a triple active bridge converter is shown in this slide, where we can see three active bridges, 1, 2, 3, or named as port 1, port 2, and port 3, are coupled together by a multi-winding transformer. The leakage inductances L1, L2, and L3 can be separately placed or can be integrated with the transformer. The bridge voltages V1, V2, and V3 are also shown. The phase shifts between the ports and the duty cycle of each of the ports are the major control variables in order to control the power transfer in between the ports. The duty cycle variables are delta 1, delta 2, delta 3, and the phase shifts are phi 2 and phi 3, and the phase shifts are measured from port 1. The triple active bridge can be modeled in a Y equivalent and then in a delta equivalent circuit architecture. We model the TIB converter in a delta equivalent circuit architecture in order to compute the current and the power transfer in between the ports. The equivalent leakage inductances, line inductances L12, L13, and L23, those are placed in between the ports, are computed here and presented. For the ease of circuit analysis, we model each of the ports as a series combination of sinusoidal voltage sources, and that can be done by the Fourier expansion of the quasi-square wave voltage shapes, which give rises to the series combination of sinusoidal voltage sources, and that is also presented in the slide. The winding currents of the three winding transformer can be calculated using this formula presented here. And also it can be computed as a summation of AK sine k omega t plus BK sine BK cos k omega t. The computation of the winding RMS currents is essential in order to correlate the winding currents with the total conduction loss in a TAV converter. The winding 1, winding 2, and winding 3 RMS currents are calculated and presented in this slide. In a TAB converter, the power transfer in between the ports can be computed as follows, and it depends on the phase difference between the ports, the duty cycles of the voltage of the particular ports, and the leakage inductance that is connected in between the two ports. The total power that is synced at port 2 and port 3 or sourced can be computed as the total power that is the flowing into the ports from the rest of the ports, and thus the port 2 power and port 3 power is computed. The generalized conduction loss optimization problem in a TAB converter is formulated in our work, where the objective function is formulated as the sum of total RMS winding current squares, which essentially correlates to the total conduction loss. And the two major power flow constraints are set by the power that is transferred to the port 2 and the power that is transferred to the port 3, and we compute them as the total synced powers at both the ports. Thus, the objective function can be minimized while maintaining these two constraints, and this will lead to the optimal phase duty control variable sets. Those will give us the optimized loss at a certain operating point set by the output port gains and the total load range. The applicability of the different phase shift modulation strategies in a TAB converter is shown here, while changing the gain at port 3. We are keeping the port 2 gain at unity and the port 2 power at 174 watt. The port 3 gain is varied from 0.7 to 1.3 while keeping the load as 50 watt. As we can see, at 0.8 gain of port 3, the DPS modulation strategy, or the only phase shift based modulation strategy, is giving us very high conduction loss correlated by the total objective function value. While the higher order of modulation strategies incorporating the duty cycles at the different ports are giving us lesser conduction loss. Similar thing is happening when the port 3 gain is 1.2. Thus, it is noteworthy that while operating the TAB converter at a non-unity gain operation, the total to supply the required power at the output ports, we need to optimize the total conduction loss by incorporating the duty cycle variables in the system. In this work, we have searched the sectors in between the load range, load and wide load and gain range, in which sector the application of which modulation strategy is beneficial in order to minimize the conduction loss, and while less burdening the controller by employing a higher order system for all the applications. In this plot, we see the percentage reduction in computed objective function under the influence of the optimal PWM strategy compared to the basic DPS modulation strategy. This helps visualizing the benefit of employing the optimized PWM modulation technique over the basic phase shift based modulation or the DPS based control. The plot also shows that the basic DPS PWM strategy becomes the optimal technique for a broader gain and load range as the output power increases from the mid to the full load for a particular port 3 voltage gain. Also, as the port 3 gain drifts away from unity, involvement of one order higher PWM technique, that is the TPS or the triple phase shift, becomes necessary while maintaining high load at port 3. And in extreme case conditions, all the port duty cycles should be incorporated in the control strategy. The experimental hardware setup for the TAB converter is shown in this slide. As you can see, we have three active bridges: bridge 1, bridge 2, and bridge 3. Bridge 1 and 2 are made of silicon carbide MOSFETs, and bridge 3 is having GaN devices as the switching device. This is the experimental setup of my triple active bridge converter. In this triple active bridge converter, we have, as you can see, three different active bridges.
This is the first active bridge, this is the second active bridge, and the third active bridge. The first two bridges are identical in nature. By that I mean that we have connected the same silicon carbide devices as the switching device in both bridges. And the third output bridge is having a high current at the output with a low output voltage of 22 volts. That's why we have connected 100 volts on high current GaN devices as a switching device. And we'll be measuring the bridge output voltages and currents through these two oscilloscopes. And this is the multi-winding transformer, the three-winding transformer, which is having a transfer ratio of 7:5:1. And the input bridge voltage, or the primary bridge, is having a DC link voltage of nominal 160 volts. The secondary is having around 120, and the third is having 20 volts nominal voltage. All the three voltages can be varied in a wide ratio of 0.8 to 1.2. In this experiment, we will be controlling the first bridge as input bridge, and the second and third as the outputs. The second bridge is having a load of 175 watt at a gain of 0.8, and the third is having a load of 50 watts at a gain of 1.2. So this is the corner case. So we'll be seeing the converter performance at when we implement the triple phase shift modulation without having any duty cycle control in any bridge. As you can see in this waveform, it is showing the primary bridge and the secondary bridge voltage and currents. There is no duty cycle control in the bridge output voltages, and the currents are having RMS of 1.1 and 2.16 ampere. And this is showing the voltage and current of the third output bridge. There is no duty cycle control in the third bridge as well, and the current is having a peaky nature with a RMS current of 10.13 amps. Now we'll be seeing the performance of the same converter in the same operating condition with the implementation of the duty cycle control.
The
With the
major
implementation of
conclusions
the
which you can
hybrid
draw
phase
from this
duty control
high temperature power
triple
conversion
application,
work
we'll see
is
that
presented
how
in
the
this slide.
RMS current can be
A
optimized at
successful
different
design of a silicon
ports.
carbide
So
paired
now
die-based
we'll be
100 watt
operating this
non-inverting
converter
buck
with
boost
the
converter, which is
incorporating the
operable
different variables
between the
in
temperature range
all
of
the
25
bridges,
degrees Celsius
and
to
we'll
200
check
degrees
the
Celsius is
output
presented in this
current,
work.
how it's varying.
The
So
parameter
we'll go to 160
characterization of
volts
individual passive
input,
elements
and
as a function of
now it's
temperature
running.
is carried
So you
carried
can
out
see
in
this
this
is the
work
primary and
in order
secondary
to
bridge.
check reliability of the
You can see the
power
currents are moving
converter power
from like
stage
1.6 and
components separately.
1.8 amp RMS.
Only a
And as you
3 to
can see in the
5% of
tertiary bridge,
efficiency drop is
in the
measured at
tertiary
highest
bridge,
operating temperature
is
compared to the
in the
nominal one,
in the tertiary bridge,
which is due
the
to the
RMS
proper
current is
choice of
having
the
a
components.
5.2 amp
Also, this work
value,
showcases
which was having
the
around 10
applicability
amps
of the
value in the
silicon carbide paired
only
die
phase control modulation.
MOSFETs for high temperature power conversions. For any further questions, you can contact me at my email sday27@asu.edu. The major conclusions from this work can be drawn as the utilization of the proposed frequency domain generalized harmonic approximation technique simplifies the multiple mode based complex time domain based analysis. The duty cycle control along with the phase shift control optimizes the system conduction loss by providing higher degrees of control freedom for a wide gain and load range. The experimental results also verify the theoretical models of the RMS current calculations and the power flow regulations. Ultimately, the implementation of the proposed optimal phase duty control brings in substantial efficiency benefit for a wide unity voltage gain condition than the conventional phase shift based modulation. Thank you for watching this video. We appreciate your interest in the ongoing research at Peace Lab. For more detailed information regarding our research, you can check out our publications at IEEE.